we transfer it into some formal representation, we do some reasoning, we generate a report, and we enter it in the patient EMR. So we are independent of that, and when it's in the EMR, it's we're done. That's and let's say so. This is more explained that there is a consultation, so the doctor talks and with the patient, and the three modalities are there. So my left ear hurts a lot in the transcript. That is captured as a triple. It is not the triple, and there's other. Your ear canal is swollen, and in general, a consultation takes about 1,000 words, more to 1,200 words, and we also get that number of triples. I have some data later, but you get a large graph over here. Then we have the guideline, the medical guideline from so the patient history, ask for whatever the evaluation. So we generate an ontology, and the ontology serves as a kind of template, fitting template for the transcript, the dialogue. So this is matched with that, and then we get an excerpt from this knowledge graph. So we end up with about 20 to 30 of the elements in the knowledge graph, and that is input for the language generator, and that generates them. Fortunately, the medical profession, they are accustomed to write very simple and short questions. So that makes our life very easy. The generation of sentence, we don't. So patient has pain and there, etc. So that's you see all. And for instance, the evaluation is just okay. Otitis externa, the ear infection, the Latin word for ear infection, at the left. That's it. And no further explanation if not needed. Very, very short. And the same for the, you see, okay, the doctor says you have a swimmer's ear, but swimmer's ear is recognized as a synonym for otitis externa. And that comes in the, over here. And the same for the treatment, drops, ear drops twice a day, etc. comes in here. So that's okay. So this is then the functional architecture. In view of the time, I will not go in all details, but you see here, say the processing from the dialogue and the interpretation, and then the enrichment, and here is the classifier that matches, and then the sentence composer. So that's the three parts. In the recording, we use as much off-the-shelf technology as possible, except for the action. Action seems to be difficult. We need to adapt it. I'll come back to that later. But Bluetooth channels is all off-the-shelf. Interpretation is we use all kind of AI technology, triple stores in Stardocs and etc. But I'll skip that. And this is the dialogue summarization pipeline where the main research question is, okay, how can we summarize the speech for the doctors? So the transcription, we currently use Google Speech, widely available. However, it is on the cloud, and for medical applications that is simply forbidden. The doctors will not accept it. So we're currently transferring it to Caldi, and Caldi is an open source natural language speech recognizer available in Dutch. And the Netherlands police is also utilizing that for automated aangifte. What's aangifte in English? Reporting of something that's utilized. So that's they're very interested in that. Typification by software from computational linguists. The Stardock graph database. We need to converse the guideline to the ontology by means of a tool from Stanford, for Protégé, from those who are working in OWL, semantic web, well known. Triple matching is what we build ourselves, and we use the generation of natural language text by Natural OWL, built by a Greek university. So, and here, for instance, you see the triplification. You see here the sentence of the care provider, how your ear canal is swollen and red, and you see here how that turns up in the canal is red and is swollen, and then we can analyze that. And similarly, as the ear has a swimmer's ear, but that is also already recognized as otitis externa. So that's very nice. And this is from our own system. So we linked it with WebFile, and you get this kind of graphs that we need to match, and this is already being reduced, but you see pain and itching and things like that. So, and this is also one of the outstanding research questions of one of the pending research questions, how to traverse the graphs to find matches. Okay, and then the report generation, that is also, that's very complex, but we use off-the-shelf technology. Okay, internally, we have developed the concept of the patient medical graph in order to have a stable system to tune our algorithms. And so essentially, the knowledge graph of a patient, the patient medical graph, consists of 5 subgraphs: the anatomy, the symptoms, the value of the symptoms, the diagnosis, and the treatment. So that's that is based on all kinds of nice anatomy books that is very well described. We do not have to do that. They even put it for us online in web services, so that's also very useful for us. And so I have again the example of ear infection, otitis externa. By now you must have recognized that we use otitis externa as our model disease. That's because it's very easy to talk about. Everybody knows it. So there are, in the amnesia, are some questions. And the physical examination, the otoscope is the, let's say, the device which the doctor utilized to look in your ears. And then you can have some kind of observations that hopefully also can be input in the EMR through Bluetooth. But this is then the anatomy graph. So you see the patient has a body and a head and eyes and ears and a right ear and a left ear and an inner ear and a middle ear and outer ear, an auricle and a helix, etc. And you can imagine that the whole body of human anatomy is, let's say, specified in this way. And fortunately, this is very stable. As humans, we do not evolve that strong anymore. Maybe for the young ones that is a pity, but for me that's a very relaxing observation. And so this helps us that this is so stable to link all the guidelines to that. And when doctors find new phenomena, then we can easily add them. And then we have the 6 graphs have the different colors. So the anatomy graph, the symptom graph, the value graph in green, and the means even in gray, the diagnosis in red, and the treatments in orange. So that you see here that we have the left ear has drainage. So this is the value graph. Drainage can have a value yes or no. Pain can have a value 1 to 10. Itching yes or no. But hearing loss from so you see all kinds of value for different symptoms. And also this can be based on the guidelines, and you can also imagine that, say, the pain symptom is very general. You can apply, you will see it at many places, but let's say where the oracle, that is pain attraction, that is very specific or whatsoever. So that's or the eardrum, intactness of eardrum, that's very specific. So, and this is then a filled-in patient medical graph where you see that this patient has a left ear, has pain on a scale 7 of 10 for 4 days, has no drainage, has mild hearing loss, has no scars, has the eardrum is intact, etc., etc. And that has let's say, led to the diagnosis of the doctor of otitis externa and with this treatment. So this is then taken from the consultation and and that is then input for the language generation. And you can imagine that you can do that at different places, and you can even do that if we are allowed to store this, that you have a refined model that you can compare these graphs over time. But that's for the future. Okay, then something on the report generation. This is the architecture that I already explained to you with. So we have the input with audio and the video over here, and also the sensor with the blood pressure sensor, thermometer, etc. coming in, the front end on WinForms, and then we have it's all programmed in C# and runs Linux Ubuntu. All intermediate results are stored in the consultation timeline in cache, and then in Stardock, and then we have all microservices. This is for the language recognition, and this is for the action recognition. At the moment, still very small, and the domotics, all the measurements are actually very simple. They give a value and so on. But again, all those green elements are third party, and all the blue ones is that what we build ourselves, and that is really a very huge architectural challenge that we need to face. Okay, the report generation on Natural OWL is taken the selection of the content, plans the sentence, and finds the words that are needed for that, aggregates them. You do not want in the report that, okay, the patient has pain, the patient has itching, the patient has this. That needs to be combined in one sentence. And then with referring expressions, so his ear, and etc. But we have a local expert on referral expressions over here, so we rely on that expertise. And the service realization, so having commas and dots, etc. if needed. And that is a very nice, so the micro-planning of the lexicalization, so you, for every, say, syntactical element, you can have a box, and so you can have multiple boxes for several sentences that can be filled. So that works very nice. It's the work of the team of Professor Ian Androtsopoulos from Athens. Yeah. And we did some experimentation with in this case, 8 otitis externa transcriptions. So we obtained them through our collaboration with the NIVEL, the National Institute for Healthcare, which is here in the city center. And so these are just some descriptive statistics. So you see that the number of words in the different is varying, but in average 1100. And for instance, nouns, that's about 100, verbs, sentences, and turns. You see also the number of turns, that is really, the dialogue is interacting and question answering. And you see also that the turns in the beginning, that the patient tells a lot about the medical history, and at the end, usually, the doctor tells a lot about, okay, gives advice, you should not swim, or you should not do that, or you can expect that in 2 weeks it will be over, and then if not, you need to come back. But this, all these advices need not to be reported. So, but for us, the nouns and the verbs are very essential for pinpointing the, let's say, the words that need to be extracted for the report. So we also did some, we had some, the medical doctors that we collaborated with also provide us with example outputs, so example reports, and our system created output, and we compared them. So we created a so-called ground truth by having just one medical doctor providing them for us, which is also a debate, of course. We should have more, and in the meantime we have more. But you see here, let's say, the usually precision recall and F1 scores with that. And so you see that R3, we're doing really good. The precision is to a very acceptable level. However, R6 was very poor. That's, and then it was also longest word, but that's, and as I think it was the Utrecht standard consultation where there was a return that somebody came for a second time, that it was not, well, in fact, or it was a multi-morbidity, so there were multiple diseases. So this really shows that, that this technology is not, let's say, to be launched in next year. We still need to do some research. That's good for us. Secondly, you see that the recall is also, yeah, so we see that all kinds of things are missing, and yeah, we really need to do much more investigation in this aspect, especially in conversation analysis. So how can we really see deeper in the structure of the conversation what is going on? So, yeah, the current prototype runs, and we have several PhD project planning. So what's in it for you? What I promised in my abstract. So, especially in those 5 areas, I can, let's say, you're willing to come to us and join our forces if you like, have master students, bachelor students. So in software architecture, with Jan Martijn and Sergio de Spagna, we were working on a plug-in architecture. The system is too complex to say, okay, we make it available for general practitioners and cardiologists and rheumatologists and you name it. We need to have some kind of a plug-in architecture. We're building that. That means we need to have a platform. I forgot to include we have already an architecture diagram for that. With the people in of linguistics, computational linguistics, we're collaborating on triplification and confirmation detection. That's what somebody says no to a specific question that is still not very well heard by our recognizer. And we have, of course, graph algorithms. I'll come back to that. Machine learning. We need to build medical action classifiers, and also the conversation analysis. I have some examples. So this is the triple identification. So how can we build triples from those sentences? How can we build identify paraphrase phrases? So the doctor has to ask for itching, but you can express itching in different ways. It feels weird. Yeah, it itches, or how many ways you can say that it hurts. That is, yeah. So we use libraries of all those paraphrases. Then this is the algorithm, the graph algorithm that I especially showed for Hans, of course, where yeah, we need to traverse, this is a breadth-first triple matching. We need to traverse two large graphs in order to get the matching and to go to 1,000 from 1,000 on the one and about 100 on the other to find the matches and to have this ontology matching really working, and that is well, you see how this is currently working, and yeah, we see that there are many optimizations possible. Also, the machine learning is very nice. So together with Albert Sala and Metehan, we are currently building a classifier with training with new ways. And Laura Schiphorst has made 550 videos of elementary actions of doctors to identify whether they are escalation, that's with the stethoscope, or whether they are doing a palpation, or they do a blood pressure measurement. So that's and the results are very nice. And currently are also working on a paper on that. And this is the for the conversation analysis, where you see here the challenge is the filter of relevant information. So when this is the consultation of 5 or 6 minutes, this is the number of words of characters. When you have those SOEP classes, that you see that in fact many parts are not relevant, and you even so how to identify those parts that are irrelevant, so that you can also reduce the graph algorithm. So that. Okay, that's it. We're working that together with Sabine and Fabiano and a lot more. These are the current papers, also with the help of Kees van Deemter, and lots of students also sitting in the back. Imam and Fabian. Also Florian is on the other paper, so we also include them as co-authors because through their work they contributed a lot. So I have some references, and then it's time for questions for you. All right.